Okay, hello everyone. Welcome to another Q&A about history of science and technology. On Friday, I had been doing Q&A and I was rapidly getting sick. I'm happy to say I seem to have been recovered. Human 1, COVID virus 0. So after 3 years, no, I was last sick in 2018. So I was a little disappointed to finally get sick again, but seem to have triumphed. All right, let's see, a variety of questions here. Blank is saying, I'd recently talked about relearning history of thermodynamics. I can ask for resources for learning the history of thermodynamics. Hopefully I will soon be able to provide one because I'm going to write something about the history of thermodynamics, probably be a few weeks out. I would say about learning this kind of history in general, you got to go back to the primary sources. There are a few summaries of thermodynamic history, which some of them are not bad, but it's just the amount you learn by just going back to the primary sources is amazingly great. And it's always interesting to see, like I've been trying to understand who really came up with the formula ds equals dq over t, the change of entropy related to the change of heat and so on. Well, it was kind of Rudolf Clausius, but he kind of did it in a complicated way. And then it was kind of other people. And who really established the second law of thermodynamics? What were people thinking about when they established the second law as opposed to the first law? There's a lot of very interesting history there. And I also find that you got to look at the primary papers. If you're lucky, they've been translated into English, at least for me. Some languages I can read, but others I can't. And sometimes you have to look at the original language and try and piece through things, looking at formulas and other such things. But I was interested to understand things like the ds equals dq over t and where'd that really come from and so on. And I discovered that the best and clearest description of this stuff that I have found so far comes in a book called The Theory of Heat by a certain James Clerk Maxwell, who was a very clear writer, very clear presenter of logic about what things really mean and so on. I must say that in this project, I've become very impressed with James Clerk Maxwell. And I was already impressed with him, but I was become even more impressed with him. It led an interesting life. We can talk about it if people are interested in that. I'll probably write about it when I write about the history of thermodynamics. It's always interesting to see these different personalities and kind of what they thought they were achieving. Clausius was not as mathematically sophisticated as Maxwell, but was, and all of these people were sort of, Maxwell was strangely practical in many ways. As the person who made what many people would be considered to be the first color photograph, for example. He was definitely had a practical bent, but you'll find even in his theory of heat, there'll be things where he says, there's the theoretical formula, such and such, such and such, but the actual viscosity of air is blah, blah, blah. And he says, viscosity has been measured for solids and liquids, have been measured by people, including blah, blah, blah. And for gases, including blah, blah, and myself, he says. And then he quotes his value for the viscosity of air and so on. So it's kind of an interesting collection, correspondence between the sort of the very theoretical and the quite practical. Also interesting that there's a charming little thing where Clausius has assumed that all molecules travel at a fixed velocity, at a constant velocity of course, they didn't yet know that molecules really existed, but in their sort of mathematical idealization of things, the molecules exist. They're going parallel to the edges of a container in a way that's very bizarrely similar to the cellular automaton models that I've studied. They're on kind of a grid. And Clausius works out various properties of pressure and things based on molecules traveling along those grid lines at a constant velocity. And then Maxwell comes along and says, no, I can actually do the calculus and figure out the whole distribution of velocity, the Maxwell-Boltzmann distribution, together with molecules going in all directions and doing all the integrals. And then Clausius is very insistent that no, really the answer is, I don't know, square root of a half or something. And Maxwell says really a 3/4. Maybe I got that the opposite way around. Maxwell observes rather snarkily, Clausius believes Maxwell cannot do integral calculus. But in fact he can. Now I think, you see Boltzmann, for example, I think was sort of intermediate in. Boltzmann was reasonably mathematically sophisticated, although Boltzmann never really believed in the continuum. Boltzmann always set up everything in terms of discrete energy levels, discrete molecules. That's where Planck kind of got his ideas ultimately for quantum theory from, was Boltzmann's formalism, which I think had some precursors in Clausius, which I haven't really analyzed properly yet, of just sort of approximating everything by discreteness. And then being able to work out like these formulas for entropy in terms of discrete counting of states. That's I think Boltzmann was sort of intermediate. Maxwell was probably the most mathematically sophisticated in a very Cambridge kind of tradition of those kinds of characters. Although subsequently, both Carathéodory and Gibbs, in their different ways. I guess Carathéodory was a little later. Gibbs probably was also mathematically sophisticated, although he took his ideas in a slightly different direction. I mean, I think one of the things that's been sort of a horror for the history of thermodynamics is that once people realized that things like, entropy is a function of state, things like this, then it becomes a big festival of multivariate calculus and partial derivatives and things, which is a way of sort of setting up a formalism of thermodynamics without really knowing how grounded you are in terms of the actual physics of how entropy works and so on. And so there ends up being this very elaborate mathematical structure that's built that I don't think actually in the end is really completely justified. But it's sort of, many of the recent treatments, by recent I mean last 50 years, treatments of thermodynamics are very much saying, let's axiomatically assume this or that mathematical structure and then build from there, and not even consider what's underneath that and what the foundations might really be like. I think, there are a lot of charming things in this history. In the 1860s, which is the real time when this was very active, there's just a lot of interesting interaction between all these different characters. And, things like Gibbs has made these physical plaster of Paris like surfaces representing sort of pressure, volume, temperature, etc., kind of characteristic surfaces of materials. And Maxwell is then eagerly sort of making his own version of this, similarly, actually physically constructing it and so on. These kinds of things appeal to me because I'm always very practical in terms of not me so much, making things out of plaster of Paris. I don't think I've ever done that, but let's actually write the code, run the thing, see what it does, as opposed to just sort of talk about it. And so I have a certain personal affinity to these kind of let's actually just do it concretely kinds of approaches to things, which, as I say, the early thermodynamicists in the 1860s were mostly into, with the exception of Carathéodory, who was much more theoretical, and that's a separate story. Well, anyway, I probably will have more to say about history of thermodynamics soon. I'm still unraveling the whole story, but I'm getting there. Let's see, there's a question here from Igor. Can you tell us about the history of mathematical and computational linguistics? Ones that study principles and regularities of natural languages. There are famous Soviet mathematicians involved, etc. Yeah, I can try, and I'm not sure. I can try and tell you a little bit about the history of this. So, I mean, the big question is, kind of, how is language has certain regularities, and what are those regularities, and how can one characterize them? And certainly there were grammarians in ancient Rome, for sure. I think even some in ancient Greece. They were describing kind of, this is how sentences look. A very famous example was what is the name? Pingala, is that right? Panini, I'm sorry, Panini, who was a grammarian of Sanskrit. And we don't know exactly when his works were from, but 2,000 years ago, plus or minus. What he was defining was, they were defining, who knows? No, I don't think anybody knows anything about Panini as a person. They were giving a set of almost aphorisms that describe possible forms of Sanskrit. Sanskrit is constructed in this way, this way, this way. These are possible sort of sentence type fragments for Sanskrit. I looked at this actually somewhat recently, and one wonders, does one have kind of a grammatical pattern in which it says, as we might do today, a sentence consists of a noun, a verb, a noun? Not quite, not as precisely as that. Even in those days, however, people were concerned about sort of the mathematicization of kind of poetry, for sort of the mathematics of prosody, of the way in which texts would get kind of scanned as poetry and so on. And there's a famous thing from ancient Indian times of enumerating the possible forms of prosody, which ends up being a story of Fibonacci numbers, and ends up being one of perhaps the earliest invention of Fibonacci numbers, was for enumerating the number of possible ways in which you could construct kind of a thing with longs and shorts and so on that could be a possible form of poetic meter. So that's a very early example, a couple of thousand years ago. And again, the idea that there would be a grammatical structure to things definitely existed in antiquity. I mean, famously, Lucretius, 1st century AD, one of my favorite kind of early statements of kind of a rule-based model of the world was Lucretius in his De Rerum Natura, on the nature of things, sort of epic poem, talks about how perhaps the world is made of atoms, and the atoms are arranged much according to rules, much as words are arranged according to rules, the rules of grammar. So he's kind of equating the arrangement of atoms in the world, in the universe, in nature, as being sort of like the way that words are arranged in sentences according to grammatical rules. So already has this idea of grammatical rules, but doesn't really have a medium to kind of describe those grammatical rules. Although, as I say, the grammarians, I think, were mostly giving kinds of patterns of, this is the way that it's right. You can say the cat ate the mouse, but you can't say eats mouse cat or something. They were saying these are correct forms, these are not correct forms, I think. I actually don't know. I realized recently I don't even know whether there were words for things like nouns and verbs in Latin. I've not heard of them, but maybe they existed. So I don't know whether there was that sort of virtualization, that kind of abstraction that came from the actual language to kind of a meta description of the language at that level. But this whole question about sort of understanding the structure of languages, had a very, very long history. I mean, I think there were sort of different aspects at different levels of language, from phonetics to the phonetic forms, to the morphology of words, to kind of the syntax, to the semantic forms, to the pragmatic forms, and so on. These are sort of hierarchies of levels of understanding which evolved in slightly different ways. So, for example, the Brothers Grimm, famous for their fairy tale collections, were originally, they were philologists, they were collectors of information about words and so on. And in particular, they were interested in sound shifts in Europe. And I guess they went and visited a lot of different kind of villages and so on, and collected both fairy tales and sounds, and were responsible for Grimm's law, which is a law about the sort of evolution of sounds in phonetics, and that was a sort of an early kind of definite statement made about something linguistic, so to speak. I think that the thing that there were sort of traditions of linguistics. The most famous, I guess, Ferdinand Saussure was one of them in the 1800s. There was kind of a, I think here's what I think more or less happened. I mean, the languages of the earth, maybe there are 7,000 of them now. Unfortunately, they go extinct at some rate. Maybe at one point there were 10,000, maybe more, I don't know. But at some moment during the centuries of colonization, one of the sort of things that happened was that people who had kind of learnt Latin and Greek and learnt kind of the idea of structured languages were sent out to go be the poobahs of colony XYZ in different places, and there were indigenous languages there, and those people would often, I think it was particularly a British and perhaps French, maybe there was some German tradition there too, tradition of, you're assigned to some place in India, and you were brought up in a fine British school tradition or something, and you will then write the grammar book of this indigenous language of that area. And so a lot of those things got produced, and this was particularly in the 1800s, mid to late 1800s, I would say. An awful lot of work was done of sort of codifying, even producing written versions of languages that hadn't had a written version in the past. And that's why a lot of languages which you kind of might think were very sort of outlying languages, how could they possibly have kind of standard English alphabet? Well, it's because they only got a written form in 1890 or something, when some random British Foreign Service person was assigned to the area. But I think that led there to be sort of this big collection of information about languages at that time. And then people were started to be interested in, so what are the common principles across all these languages? And there'd been very much this kind of idea of sort of this descriptive tradition of writing grammar books and so on that had existed. The sort of the modernization of that, big sort of moment of that, was in 1956, when both the Backus-Naur form for computer languages and the generative grammar idea of Chomsky what's his name? Chomsky's former advisor at University of Pennsylvania. Oh my gosh. Maybe this is what having been sick for a few days does to me. My memory gets blown up here. But sorry, I'm not remembering his name. But in any case, this idea that emerged of kind of this sort of formal description of a language in terms of this kind of structure, this kind of phrase structure description, that the language is made up of sort of tree-structured things, and they're all sort of plug compatible. That's something that was sort of this more computational framework, was something that emerged in 1956, both in the context of computer languages and in the context of human languages. And that kind of then started this whole sort of revolution in linguistics, in which the more descriptive linguistics that have been done in the past kind of gave way to this more kind of formulaic linguistics, huge wars happened, and new linguistics departments got minted. Some of them have now died, but that was kind of the big transformation there. Now, into the middle of that, there was a tradition. There was also a Russian tradition that the person asking the question was mentioning. I don't know all of that, but Andrei Kolmogorov, really mostly a probabilist. One of the things he was very interested in was in language, and in studying the kind of mathematical and probabilistic structure of language, and of seeing sort of how language can have things put together. Now, one very famous paper called Three Definitions of the Amount of Information, which is trying to sort of work on the mathematicization of kind of the information content of language. And, you know, Shannon, for example, in the 1948-ish, I think, had written his paper about information theory and had this sort of P log P definition of information based on essentially taking a digital transmission line and saying, break the bits that are being transmitted, like kind of like, you know, ones and zeros being transmitted into blocks, and start asking questions about what the frequencies of different possible blocks are and so on. And I think, you know, Shannon worked during the war on cryptography and so on. And I think this kind of idea of sort of amount of information was something very important in cryptography, because if you're trying to find a key of a certain size, you just can't find that unless you have the appropriate sort of amount of information. It just you have to, that's sort of a baseline thing that you have to achieve. But Shannon really was thinking about the transmission of ones and zeros and so on, and not so much about the meaning of what was being transmitted. Now, in his original paper, one of the examples he does give is about the kind of structural redundancy of English. It's like you've got English letters, A's and B's and C's, and, you know, every time you have a Q, you have it, it's followed by a U. So there's redundancy. Every time you don't really need to record the U because after the Q, because you know it's going to be there. And that redundancy is what makes it, you know, we know that E's are more common. E's are the most common letter, followed by T's and so on. That's why in Morse code, we encode you know, an E with a dot, a T with a dash, and then, you know, a Z with some long sequence of four symbols and so on. And so this idea that you could take something like English and compress it and ask the question, how much it can be compressed, by saying, well, we'll just use these code words in Morse code, or we'll omit the U after every Q and so on. How much compression can you achieve? And Shannon argued that it's about 50%. And there's a variety of ways you can kind of see that for yourself. Like you take an English sentence, you just start zapping letters, and you see up to what point can you as a human kind of vaguely looking at it still more or less understand what it's saying. You could also, Shannon had a nice example in terms of crossword puzzles, in which he says that if you want to have an n-dimensional crossword puzzle, you want to have it be reasonably dense. So you've got words following it. You're not just having a couple of words that cross over and then the rest of it is all blank space, but you want to have it reasonably dense. Then for two-dimensional crossword puzzles, a half is kind of the critical redundancy, and that's more or less what you have in English. If you want to have a three-dimensional crossword puzzle, you need a lower redundancy, because in a sense, if you have no redundancy at all, it means that every sequence of letters is a valid word. So you can always have this kind of a completely dense crossword puzzle. I believe that's something you can do in Chinese, if I'm not mistaken, where you're using ideograms rather than letters. But in the claim will be that you can't really make a dense 3D crossword puzzle in English. So you know, that was another kind of tradition there. But then Kolmogorov was interested in going beyond kind of the pure this is how the letters occur statistically, and saying more about sort of what they mean. And that led him to his version of algorithmic information theory. My friend Greg Chaitin had a different version of algorithmic information theory. In the end, they sort of boil down to the same. But the idea is, well, just ask the question, what's the shortest program that allows you to generate the thing you were going to say? And that short program might be, you know, it's pi, and then the thing you generate is all the digits of pi, or it's something that is going to generate some kind of textual thing. And that's part of that work of Kolmogorov's. But I think in terms of the history of computational linguistics, the there's this, first of all, there's sort of the descriptive version of given something like a text in, in Caracal Pack or something, what is the, how can you describe this? Do you describe it as, a phrase structure grammar, and it's got functional heads, and it's got, adverb clauses and postpositions and prepositions and, all this kind of structure? Do you describe it in those terms? That's sort of one form of computational linguistics. And then another thing is, and can you understand what it means or translate it into a different language and so on? By the way, in terms of the exploration of languages, I sort of forgot to mention that in addition to the kind of the Foreign Service crowd and so on that were going out and doing kind of administrative colonization of the world, another very big source of linguistic knowledge is missionaries. And that's been, in fact, even to this day, the best collections of data, they called ethnologue, for example, that was constructed by those folk. That's sort of an inventory of the languages of the world. I did find it interesting. I remember a little while ago talking to some of those guys and seeing for some reason some job ad for studying linguistics and so on, and ability to fly small planes, particularly seaplanes, an advantage, because you're going to be flying up the Amazon and trying to visit folks there who have all sorts of interesting languages. But it's kind of a very action-oriented profession, I think, going into record sort of out in the field languages which still have not been well recorded. But I think in that's another tradition, and there's sort of a different piece of that tradition, which is translating the Bible into all possible languages. I don't know how far that's got. It's certainly far from the 7,000 languages that are known, but sort of first step is to even find out what languages there are and where are they, and so on. So I think it's been a thing that has been something people have been watching in recent years, is the kind of the extinction of languages and endangered languages and so on. And there are a variety of initiatives to try and sort of save endangered languages. It's a tough business because there are often languages where, people used to speak them, the older people speak them, the younger people are watching television shows that were made in the US or something, and they're going to learn English, and they're going to go off to the cities, and they're going to be doing things where they're mostly speaking in English or in whatever language it might be, Portuguese or whatever it is, and they kind of forget the native language, so to speak. And by the time you have few enough speakers, by the time you've only got one speaker of a language, it's sort of all over. And the question of sort of how you preserve kind of endangered language is an interesting question. And I know that people, someone I know has I don't know what's happened to that initiative, actually, had an initiative based in the San Francisco area of literally getting little groups together where people would learn some of these endangered languages just to have a living version of that language sort of preserved in some way. But anyway, in terms of the history of sort of linguistics, there's this whole descriptive area. Then there's the whole area of really make a computer do something with linguistics, and sort of that got a big boost in the early 1960s when there was a big sort of DARPA project to try to make an automatic translation system. And people at that time were very big on AI. AI was going to, it was all going to get solved real soon. It was going to be, it was just a question of applying computers, and pretty soon we would have artificial brains. And at the time, this was sort of middle of the Cold War, one of the big issues was, people were very worried about the following scenario. It's like, Soviets and Americans get together, and the principals on each side don't speak the other's language. So there have to be interpreters, human interpreters, that are interpreting between them. And one leader says, we insist that you remove your missiles from whatever. And the person who's doing the interpretation translates that as, you rascals, you shouldn't do this, that, or the other. And, the concern was maybe a whole war would be started because some interpreter would mistranslate at least the nuance of something that was said in Russian or in English. And so the idea, which in retrospect doesn't seem that good, was let's have a machine do the translation instead. That way there will be no possibility of error and no possibility of an interpreter kind of throwing the world or the war or the race or whatever. So anyway, there started this big initiative to try and do automated translation. It was not terribly successful, but that was a big boost to the whole concept of computational linguistics. The sort of big, I would say, thing there was, what is the target for computational linguistics? You start with a sentence in English. What does that sentence turn into? Now, what we realized in building Wolfram Alpha, we have an answer. The answer is we're trying to turn it into our symbolic language, our Wolfram language, our computational language. That's the target. So when we say, how far is it from Moscow to New York, that's turned into geodistance of entity, city, New York, blah, 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 and we have a target. And that means it's a very well-defined problem to do natural language understanding. But that target really hadn't existed before. And so there was a lot of very confused work, I would say, in my opinion, done in kind of what's the point of computational linguistics. And so one thing is, for example, generating parse trees, being able to say, this sentence can be parsed into a noun phrase, a verb phrase, a noun phrase, and so on. We have a function text structure in Wolfram language for doing that. I think it is of interest to people for sort of educational purposes. I don't think it's of that much practical importance. But that became sort of a big thing in computational linguistics. Now, I have to say, I will tell a bit of a story from, when was this? This is probably 1983, 4 time scale. I visited a then sort of vaunted AI group and university. And they said to me, we're doing a lot of exciting work here. We have a program that does language translation. And I'm like, really? That's very surprising. That's, this is 1983 or something, and you don't get to do automated machine translation in 1983. It just wasn't a thing, even close at the time. They said, no, we have this thing, and it does, machine translation. I said, okay, great. What languages? It says, well, from Spanish to English. I said, okay, fine. Can I try it? And it's like, I don't know much Spanish, but let me try it. I said, well, no, actually, it doesn't do just free-form translation. It translates stories from Spanish into English. I said, okay, how long do I have to, how long does my text have to be to represent a story? I said, well, no, that doesn't really do that either. It translates particular kinds of stories from Spanish into English. Okay, fine. Well, what do they have to be about? Well, actually, it doesn't even do that. Actually, it translates one particular story from Spanish into English, at which point I'm like, what the heck is this? What is the scientific thing that you learn from? This isn't a system. This isn't a computational system. This is at best some kind of sort of analysis. And that's what it was kind of an analysis of, we've got this one story in Spanish. Here's how we break it down in sort of computational elements and see what the corresponding elements are in English. I think that's what it was. Either that, or it was just it was kind of a fake project or something. But it was being done by sort of the leading, well, at least one of the leading sort of AI groups at the time. But so that was kind of the state of the art at that time. And of course, the modern, there was a lot done on kind of more, some rule-based translation, and then more recently, statistical and machine learning type translation, where what one's doing is to basically learn these correspondences between languages and having a neural net sort of interpolate between these languages and see the correspondences. And it's very convenient that, for example, It's again a sort of a political source. In the European Union, for example, there are endless legal documents that have been parallel translated into all the different languages of the European Union, and that's a great training source for machine learning systems. Another big source is computer manuals. There's a consortium that sort of collects all the translations of different computer manuals into different languages, and so there's some languages going to get left out by all of this, but at least you get a lot of parallel texts that way, and that's although sometimes perhaps the kinds of translations that you get might have a certain tinge of either computer manualism or legalisticism, or EU policy stuff or something to them. Let's see. Well, that was a little bit anyway on the history of linguistics and computational linguistics. Let's see. There's a question here just came in from Anne asking about the R programming language, about which I know rather little. And what do I think about the science of statistics in general? How similar is AI to statistics? Okay, so let's talk about statistics. Statistics originally was sort of numbers associated with the state, and the state as in the state run by governments and things like that. I think, what was it, John Graunt, right? The Bills of Mortality in the 1650s, maybe, was a very early example of kind of statistics. And during a plague in London, he did this grim thing of sort of tallying up the dead and giving percentages, what fraction of people, maybe it wasn't even during the plague. No, I think it was, but it's a thin booklet, and it has kind of statistical data on kind of, this person died of this, that person died of that, that person was this age when they died, and so on. And in this borough of London, this person, this happened and that happened. So that was an early example of kind of sort of tallying things up statistically. Now, I guess that also in the 1600s, through particularly the Bernoullis, there was sort of early ideas about probability, and somewhat, I think, driven by games of chance and trying to figure out odds in games of chance and so on. This kind of the notions of probability started to arise. But then when it came to the analysis of data, I think that came really a lot later. I mean, people like Gauss, for example, when Gauss was doing astronomy and, he discovered the asteroid series, one of the things Gauss did was to look at sort of errors in observation, and that's how he ended up with the Gaussian distribution, was sort of quantifying the errors of observation. And this was, I don't know, mid-1800s or so, that he noticed. Now, things didn't really get, I think, more organized in terms of statistics. I mean, there had been people who had made kind of digests about the world that were sort of a statistical nature, like Playfair is a famous person who did that in the 1800s. The Statistical Breviary, I think it's called, is kind of a summary of lots of charts of the price of this versus this, and the size of the population of this country versus that one, and so on. But that was more kind of descriptive, sort of these are the numbers, and these are some actually pretty good charts that Playfair has that represent those things. I think the origination of more sort of inferring things from numbers is something came a little bit later. I mean, Gauss was early to that game with the Gaussian distribution and so on. I think that the real sort of flowering of that came in the 1920s and 1930s with the development of agricultural research, and particularly people like Fisher and so on, who in England were studying the question of how should you best breed crops, how should you make more efficient, how should you create more efficient crops. People have been worried that the world would run out of food if the amount of food production per acre was not increased. And so that was well, how can you do that? What traits would be good for crops and so on. And so people started, in fact, there's a place near where I lived when I was a kid, actually, that was the Rothampstead Experimental Station, which was a place where there would be pieces of fields where people would, on this piece of the field, you would put this fertilizer. On this piece of the field, you would put this type of seed and so on. And then you'd measure from these little patches of field, which one grew faster, which one didn't, and so on. And I think that was kind of the development of a sort of mathematics around that, which happened in the 1930s. That was kind of the origin of a lot of what, unfortunately, one still would say is modern statistics. Now, talking about statistics, features of the state, I mean, another big piece of that was censuses, and the US was surely the leading country in terms of having a census efficiently done. And that was, since the concept of taking a census was kind of burnt into the Constitution of the US, that was something that sort of the US has taken seriously. I mean, there have been censuses done for a long time. I mean, whenever people tried to levy taxes, they would take censuses, and that happened certainly in antiquity. And in England, for example, the Domesday Book from whenever 1080 or something AD is an example of some kind of census. But the US was certainly the most organized census taker, I think. But again, I think that census was more like, well, how many people are there here? Not let's make a statistical prediction based on this. That really was something that was more came out of this kind of agricultural research side of things. And so what got invented then? Well, things like the analysis of variance, ANOVA, things like, well, I think the student t-distribution from Gossett, who went under the pseudonym student, all of these things, the F-ratio distribution, all of these different sort of tests. I hate these things, by the way. So to make no mistake, I as far as I'm concerned, by the time things descend into we're going to use this very elaborate statistical technique to tease some actual structure out of this data, you've lost the game, in my opinion. The chance of that being significant is low. But that whole tradition is what led to sort of the current practices in a lot of medical research of p-values and all this kind of thing. Came out of that agricultural research in the 1930s and so on. I think what then happened was, by the 1960s, people were starting to use computers seriously to automate those kinds of techniques. And there were early SPSS, the statistical program for the social sciences, developed in Chicago. I think Norman Nye was the developer of that, if I remember correctly. That was in the 1960s. And that was something that was developed, on mainframe computers. And kind of the idea was, take all these things that had been done by people like Fisher with mechanical calculators and put it on a computer, and put all these obscure statistical tests on a computer, and have a big inventory of, oh yes, my favorite test is the such and such named test. Let me now implement that on a computer. And so that kind of thing got done. SPSS as a company, it eventually got bought by IBM many years later, but there was a certain, I think in the 1960s and early 1970s, a lot of kind of survey taking. It was a big sort of thing of survey taking in a lot of kinds of fields, whether in politics or in marketing, and that sort of a lot of that fed into SPSS. I think also SPSS in some way managed to get, oh no, that was SAS, that was a subsequent product, I think became significant, particularly because it provided some analysis of the flow of data through mainframe computers as another sort of application of statistics. And that happened to be something that people kind of needed on big mainframe computers. But those systems, I mean, eventually started to get connected to graphics. And in a sense, that was sort of the next big epoch of statistical analysis, and one that I think is much healthier, which is rather than the weird name test that came out of a paper from 1942, is just plot your data in a reasonable way and see whether you can see certain effects or not. And it became so much easier by the time kind of computer graphics became sort of a routine thing. And that didn't really happen. Well, when did that really happen? I mean, I first used sort of computer graphics. So okay, when I first used computers in the mid-1970s, it was still the case that the typical plot that you made, you would get data from a computer, and I would by hand take those numbers and plot them on graph paper. Now, then you started being able to display plots on line printers. It wasn't really a line printer couldn't display a plot as such, because a line printer was just displaying kind of character-based data. And then there were Tektronix oscilloscope display scopes where you could sort of draw an arbitrary curve. That was something that had already existed, I think, by the early 70s. And then there started to be, I remember, the Printronix printers, which were dot matrix printers that were kind of like line printers, but you could address every dot on the page. And so then you could draw these actual graphical lines. And then another technology was pen plotters. I certainly used those, where you were, again, XY pen plotters, you were addressing the position. But there was a great tendency, I think, for those things. Well, no, actually, by 1978, I was definitely using pen plotter type output as a way to do visualization of sort of statistical type distributions and plotting things like histograms and so on with pen plotters. And I think, you know, that was sort of the next big thing, was in the 1980s and so on, was this idea of just use visualization. Don't try to assign the number 3.7 to your data. Instead, just look at your data and see, are there 3 lumps in your data or not? And I consider that a much sort of healthier approach, although sometimes as things get more sort of regulatory and so on, it's more like you've got to have a number, you know, what is your number type thing. I would say that what's happened in AI, some aspects of modern machine learning and so on is very related to statistics. I mean, it's very, you know, what one's doing in a sense is sort of giant interpolation of high dimensional data and so on. What one's doing in things like anomaly detection is things which are fairly traditional statistics kinds of questions. You know, but the framing is a bit different. The methods are a bit different, mostly. There are places where there's overlap. I mean, there's decision trees are an example of something that sort of show up in both areas. I think some of the yeah, I mean, one doesn't see, you know, it's not like people say it's a cat and with a chi-squared of such and such. People say, you know, it's not the kind of thing that comes out of a machine learning system. There are ways of doing various kinds of, well, what was the most significant feature in the image that led you to conclude it was a cat, things like this. But in a sense, the tradition of statistics, yeah, I think this is an important thing to say. The tradition of standard statistics, 1930s style statistics, is there is an underlying distribution. It's a Gaussian or something. that is reality in some sense. We get certain samples from that population of data. It is our job to try and find the parameters of the sort of ground truth by sort of fitting things. And that's what the role of statistics is. Now, that sort of assumes that the underlying is a Gaussian or whatever. And it also assumes that there's a representation of the world in terms of what's essentially a formula. And, you know, Gaussians are popular. The central limit theorem says they are sort of the thing that arise in many cases, but they're certainly not everything that can arise. And no doubt a lot of silly mistakes have been made in statistics from sort of assuming that everything is a Gaussian when it's not. But the fundamental assumption is things are fit by a formula. There's a distribution, it's determined by a formula. Now, the thing one realized subsequently is programs are a better model for many things in the world than formulas are. But so then you have the question, well, let's say you're trying to fit the parameters of a program to data. How do you do that? That's something I was interested in from my own work in the behavior of simple programs. And, you know, given this data, what simple program corresponds to this data? Those kinds of questions. But in some sense, you can think of sort of the deep learning, machine learning, neural net world as being answering a very specific version of a find me the best program that fits this data. You know, it's interesting in Wolfram language, for example, we have a function called learn distribution, which can learn the distribution of anything, images, sounds, whatever else. It learns these, you know, that you can learn. There is a concept of distribution, not just for numerical data, like in the Gaussian, but among the space of images, for example. And that's something which with sort of modern machine learning, you get to address. But by the time you're saying learn distribution, you have many of the same issues that you have in sort of traditional statistical distributions. You know, you can find random variates, you can find effectively confidence intervals, you can find, oh boy, we have a great name for this, and I've now forgotten it. The probability, given a distribution and given an instance of a thing, what is the integrated probability of everything less likely than that thing? So in other words, how outlying is that thing? If we learn the distribution of cat images, how unlikely is this picture of a cat with a crown or something? That characterizes that. Anyway, so that's a little bit about statistics. Let's see. Ethan asks about the AI art revolution that's taking place. Was there a time like this? You know, this whole question about computers that create artistic forms is, you know, has a very long history, going right back pretty much to the beginning of computing, of let's, you know, produce something that has artistic output. I mean, even, you know, Ada Lovelace, writing about these things in the 1840s, was talking about the possibility that computers might sort of compose music. And, you know, she has this great quote about how the analytical engine, you know, weaves algebraical patterns as the Jacquard loom weaves patterns of birds and flowers. But she had the idea already of using sort of algorithmic processes to produce musical forms. That, I mean, one might argue that composers like Bach and so on, you know, had sort of some algorithmic ideas, but obviously not using computers as such. And the mechanical computing devices were numerical ones for the almost without exception. I mean, I suppose that one could think about, I don't know whether anybody did this, but certainly the automata that existed from the 1600s on of the little you know, figurines doing things and so on, and the music boxes and things like this. One could imagine those as a little bit like kind of algorithmic generation of musical form, although they, I think, were very specific mostly of having a very particular kind of, you know, card-like way of specifying musical notes that didn't didn't have any possibility of sort of creativity. But as soon as when there started to be computers, there started to be the possibility of creating artistic forms with them. I remember the first computer I used, 1972, this thing called the Elliott 903. I think I even wrote some code that, so one feature of the computer was that it had a tone generator. It's something that sort of got lost in subsequent generations of computers, but as it would whistle while it worked, so to speak. And as it was processing data, it would be, it would make all kinds of noises. It was never completely clear to me what those noises came from. And I looked in its documentation to figure out, what generated the noise. And I don't think it ever said. And I should ask somebody. There are still people who are enthusiasts of the Elliott 900 series computers. I should finally find out what did the noises come from? Because what I did was I sort of empirically figured out, based on actually running tight loops in code, okay, that tight loop makes this sound, this loop makes that sound, and depending on the tightness of the loop, you can make a different pitch of sound. But I don't think I did anything very profound, but I certainly made things that would generate sort of semi-random sequences of musical forms. So that was definitely a thing, and it was the idea that computers might be able to compose music and so on. Definitely a known thing. In 2001, Space Odyssey, there's sort of a scene of HAL, the computer, showing sketches it's made and things like this. No, maybe it's commenting on a sketch somebody else made, but I think it has. Does it create art? It does something. It makes a tune or something like that. I'm forgetting slightly. But in any case, it is definitely a known idea. There were composers, I think Xenakis was one of them, who were quite into sort of algorithmically generated music. I think even used some things came out of my sort of cellular automaton investigations for that. In music composition, for example, we had this little project in 2007 called Wolf and Tones, which is used cellular automata to make pieces of music that are kind of interesting if you only, at least for 15 seconds or so. And I've been told that it's a pretty good source for people who want kind of compositional inspiration, so to speak. There are also sort of different traditions of taking sort of existing music, classical music, for example, and saying, let me sort of grind that up into pieces and reconstitute it and use that as a sort of statistically constructed sort of Bach-like piece of music. That was a different tradition. That tradition is probably more like the tradition we're seeing now in terms of kind of visual, and I've seen less music actually along these lines, but visual scenes where basically one is sort of grinding up the visual scene and saying we can reconstitute it to have to be something that is a reasonable guess for what a sort of full picture might be like. But in terms of this idea, I mean, one has seen computer art of various kinds forever and ever and ever. And this concept that it is sort of derived from these distributions that effectively come from the real world, I think that's kind of a newly doable thing. I think that's not something that's been possible before. In the past, sort of the computer art, so to speak, has been much more take things that are mathematically defined, for example, and be able to add some randomness to that, and then say, this is the thing we're producing. There's a sort of seed of randomness, and then there's a whole sort of development that is mathematically defined, and that's the artistic form. Whereas what we're seeing now is there's a seed of randomness, but the development is more in this sort of ground up interpolation of real world scenes. And so yeah, I think that's I think that's kind of a new thing. I'm trying to remember whether there are previous versions of this that one's seen. I mean, certainly there are kind of, in from the sort of the Photoshop style of image processing, it's been the case that there've been sort of fill-in things where you're sort of filling in a piece of a scene to sort of follow that thing that was supposed to be a picture of a tree, but that part of the tree got cut off and now you want to fill it in again. That's been a thing for a decade-ish. But now it's kind of like just take the whole picture and say, I want a tree, and you can sort of generate that from on its own. Now, I have to say, some of these things that I see are, I kind of, it's like, well, it's very cool. It's a very good demo. It's not quite as impressive. It's like, look, I could just do a web search for pictures of blah, and I would get a bunch of pictures. And now the question of how they merge together, that knitting together, that interpolation together, that's kind of interesting. The just do what we'd expect kind of thing is working really very well in many ways. Although, I don't know, it's hard to know what the definition of success is, because is the definition of success we like the picture, or the picture kind of is a sort of a fake that passes muster for some particular thing, or what? I mean, for example, a little while ago, somebody was telling me about the wonders of, I think, GPT-3 text generation system, and was showing me some sort of simulated conversations between various sort of scientists of old and so on. I was looking at it, and it's like, oh, this is kind of cool, and it's reasonably, maybe it's reasonably convincing. I said, can you do one of these for me? There's enough of me on the web, and texts from me and so on, that you should be able to get a pretty accurate language model for me. And so they did that. And then there's a thing, answering questions as me. And I look at these things, and frankly, I thought they were terrible. Now, I couldn't tell they were terrible if they were answering questions like, I don't know, Kurt Gödel might have answered questions or something, because I know a certain amount about, actually, even that one I might have been able to tell, but I think it was people where I didn't really know their style very well. But by the time it was trying to imitate me, and I sort of know my style for better or worse, it's like, this is terrible. It sounds, it's rambling. I might ramble, but it's rambling off in all kinds of directions, and it doesn't really, there's no thread of the point and so on, and it really, it's saying things in ways that I would never say them, and so on and so on and so on. So, from a distance it would look fine, but from close up it really didn't look very good at all. And I think the same is often true of these visual constructions. They're very interesting, and they're very they're kind of like, there's a new generation of art that will be produced this way. But one of the issues always with art is, so in a sense, what's the in some sense, what's the point? And if the point is human sort of satisfaction, engagement, whatever else, that's a fine point. But it's hard to measure that very precisely. It's hard to say we achieved, 9 out of 10 for our art. That's hard to quantify in that kind of way. Oh my, there's all kinds of interesting questions here, and I'm about to get to time when I have to go back to my day job. I think we have another live stream coming up about day job kinds of matters. There's a question here from David. Let's see if I can talk about this one now. And there's a lot of other interesting ones here that I should attack another day. David asks, what did Henri Poincaré think about the infinities considered by Cantor, Hilbert, and Zermelo? Do engineers need the concept of a complete infinity? I do not know what Poincaré had to say about Cantor. Certainly must have been aware of him. And Zermelo was surely very much in that orbit. I mean, Zermelo was in Switzerland, Poincaré was in France, Cantor was in Germany. And this was all happening 1880s, 1890s, that kind of time frame. I don't know. I think, I mean, Poincaré, in a sense, Cantor, there's a certain thread of development towards the sort of formalism of mathematics, a sort of formalistic view of mathematics that goes from people like Frege to people like Whitehead and Russell and Hilbert. And Cantor was sort of a sideshow to that, but not really a mainstream part of that. Poincaré was very much against that and thought of mathematics as I begin to think of it now, as I've sort of been studying the physicalization of metamathematics, of mathematics more as a sort of a high level, kind of humanistic level activity, far away from the kind of formal level of axiomatic structure. But I think, you know, Cantor was really a different branch there. I mean, in a sense, Cantor, in the end, mathematical logic sort of connected with Cantor, but it was not its earliest part. I think that Cantor and his notion of transfinite numbers and so on, it's always been an interest, because it's one of those things where it was invented in the 1880s, and you know, it's now 140 years, whatever it is. And the question is, did it matter to things that people in practice do? Because people often think, you know, mathematics that is aesthetic enough will end up having an application before too long. But transfinite numbers, it's not clear what application they've had. I have to say that well, I've been interested in applying transfinite numbers. But the history there has been that in set theory, for example, transfinite numbers are, yes, I mean, okay, so yeah, that's right. The emergence of transfinite numbers meets mathematical logic, that really happens in set theory, which is not surprising because Cantor invented set theory. That was, you know, Cantor was originally studying the somewhat prosaic question of the convergence of trigonometric series. If you have a sum of sine of, you know, square root of blah, 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 sine this, that, and the other, what is the region of convergence of that series when you sum it to infinity as a function of parameters? And Cantor realized that you could have really complicated regions of convergence and so on. And it was from that he invented set theory, and transfinite numbers came out of that. And so Cantor was the originator of set theory, and set theory got entrained in this whole kind of formalization of mathematics. Although in the earliest versions of things, you know, there were sort of logic was one branch, pure arithmetic, things like that, another branch, and then set theory, which had come out of and was deeply related to, in its upper reaches, was deeply related to transfinite numbers. But now you can ask the question, did transfinite numbers as such end up being something that was important for practical sort of things in mathematics? The answer is important in set theory, lots of discussions about, you know, large cardinal axioms and things, lots of theoretical discussion. In terms of, and did it matter for building rockets or something? The answer to date has been, I think, no. I mean, there was a claim for a little while that in high frequency trading, people were using transfinite numbers, but I think that was more a decoy than it was reality. I think that for myself, the thing we've been interested in for Wolfram language is we have lists, finite lists of, you know, the list X, Y, Z, 1, 2, 3, whatever. Now, what happens if we have an infinite length such list? And are there different kinds of infinity of the length of that list? And how do we know whether two infinite lists have the same length? And if it isn't an infinite list, but it's an infinite tree, how do we compare infinite trees to infinite lists? This, I think, leads one into sort of stories of transfinite numbers. And perhaps in the next few years, we'll actually have a sort of practical, symbolic version of transfinite numbers that one will be able to that will end up being of practical use, where we'd actually have a transfinite omega or something as a symbol, just like we have the symbol infinity in Wolfram language. But in terms of to my knowledge, to date, none of that stuff has had direct engineering consequence. I mean, there's been sort of attempts to say, let's do validation of things like blockchains and so on the basis of a logic that's ultimately sitting on top of set theory. But I don't think that's gotten that far. It's sort of an interesting but very distant possibility, and it won't solve the problem of saying, oh, we base everything on set theory, so then we've solved all of the kind of governance problems of blockchain. Hardly. That's sort of a different branch. It's a different set of objectives that are being achieved there. All right. Well, I should wrap up here. I think I can tell that I'm probably sounding not my usual my usual voice pattern and so on. I suspect it's the tail of the viruses and so on, although they don't seem to be that serious. Well, thank you for a lot of interesting questions, and I see a lot more, and I look forward to continuing in another couple of weeks when we get back to that part of our cycle of live streams. And as I say, I'm about to go off and do a day job live stream for those who are interested in that in just a few minutes. So thanks for joining me, and bye for now.